Welcome to the lecture series on CFD Part 2. This is lecture 34 on grid quality metrics and analysis. This lecture is devoted to grid quality. Discretization errors in solutions obtained on grids with the same number of control volumes may differ by an order of magnitude. It is therefore important to pay attention to grid quality. Some grid quality parameters are obvious, like control volume non-orthogonality, cell expansion ratio, and cell aspect ratio. Others, like cell warpage or roughness of discretized curved boundaries, are more difficult to quantify. Special attention is paid to prism layers and sliding interfaces. Some other grid quality issues are also mentioned and demonstrated with suitable examples. For a given selection of approximations for the rate of change, convection, diffusion, and source terms in the conservation equations, discretization errors are reduced by grid refinement. The rate of error reduction depends asymptotically on the order of approximations. However, the initial level of discretization errors depends on grid design and quality. For the same number of grid nodes or control volumes, the level of discretization errors on two grids with a different design and quality may differ by as much as an order of magnitude. It is therefore important to pay attention to grid quality and local refinements when generating the initial grid. For a reliable assessment of discretization errors by grid refinement, it is important to keep the grid design the same for all grid levels. For an accurate approximation of convection fluxes, it is desirable that a straight line connecting two neighbor cell centers passes through the center of the cell face. The highest accuracy of diffusion flux approximations is achieved if the line connecting cell centers, in addition, is orthogonal to the cell face. See lecture 23 for a description of some approximations. A triangular in 2D or tetrahedral in 3D grid can be orthogonal in this sense. This figure shows two control volumes from two-dimensional triangular unstructured grids. One is non-orthogonal, with cell face normal, making an angle theta with the line connecting cell centers on either side of it. The other is orthogonal because the line connecting cell centers on either side of the cell face is orthogonal to it. In complex geometries, non-orthogonality often cannot be avoided, resulting in situations like in this figure. This is usually the case near sharp corners when boundary-fitted structured grids are used. In unstructured grids, prism layers along walls are affected by this issue. This will be shown in the next slide. The worst situation related to cell non-orthogonality results at sharp edges on walls when prism layers wrap around the corner, as indicated by this sketch. These two cells have a common face, but cell centers are too far away from the face center, and the line connecting cell centers does not even pass through the face. Using linear interpolation from values at cell centers to compute the value at face center is highly inaccurate because of different flow directions at these locations. An example will be shown on slide 9. A strong non-orthogonality can also result at non-conformal grid block interfaces. For example, if one grid block is sliding along a fixed grid and cell aspect ratio length to width is high, as indicated in this sketch. These two control volumes have this common face, and the line connecting cell centers is highly non-orthogonal to it. Several adverse effects of control volume non-orthogonality may be encountered. One is convergence problems, requiring lower under-relaxation parameters and leading to a higher computing effort. Another possible problem is oscillations in the solution, which can violate boundedness criteria, for example, resulting in negative values of physical and non-negative variables like turbulent kinetic energy. Local grid adaptation can reduce the adverse effects of control volume non-orthogonality. One possibility is to minimize the distance from face center K to the point K prime at which the line connecting cell centers passing through the face. For example, if the quadrilateral control volumes from the example shown on slide 5 are twice refined only in the direction parallel to the face at which grid line changed direction, an improvement is achieved. The point at which the line connecting cell centers on either side of the common face passes through the face is now much closer to the face center. The effects of grid non-orthogonality at a sharp boundary corner are studied on the flow through a channel with a forward step. A reference solution is generated by using a fine Cartesian grid, locally refined at the step and along walls, which is finer than trimmed grids with control volume non-orthogonality at corners that will be used to assess the effects of cell non-orthogonality. This plot shows details of the reference grid near the step. The channel height before step is 50 mm and the step height is 20 mm. Fluid is water with density ρ equal 1000 kg per cubic meter and dynamic viscosity μ equal 0.001 pascal second. Inlet velocity is 20 meters per second, which leads to a Reynolds number of 1 million. Leg EB K epsilon turbulence model in SimCenter Stasis and Plus software was used with second-order discretization for all terms in equations. These plots show details of the reference solution near the step, flow pattern, pressure contours, and contours of turbulent viscosity ratio, that is, the ratio of turbulent viscosity to fluid viscosity. The flow is from left to right. A high pressure zone results in this corner, which leads to a clockwise recirculation zone, which is clearly visible in the flow pattern visualized by line integral convolution plot. Above the protruding corner, a low pressure is created. The favorable pressure gradient along the upper part of the step wall results in flow acceleration toward the corner. Fluid cannot turn immediately at the sharp corner and therefore separates at the step edge, forming a large separation bubble and thus reducing the effective cross-section area for the primary flow. The reattachment point is circa 2.6 step heights downstream of the corner. Turbulent viscosity is highest around the reattachment point and downstream of it, where it is about 8,800 times higher than fluid viscosity. This slide shows details of 4 trimmed grids with prism layers along walls used to compute the flow and assess the effects of the grid non-orthogonality at the step edge. This is the coarse grid with 6 prism layers along wall generated by the automatic meshing tool in SimCenter Stasis and Plus software. This grid is generated using the same setup, but the cell size is halved compared to grid 1. Both the non-orthogonality and the cell aspect ratio, that is, the ratio of length to width, remain the same after grid refinement. In grid 3, the cell size is again halved relative to grid 2. This grid is identical to grid 3 except for 2 levels of local refinement at the step corner. The non-orthogonality remains the same, but the aspect ratio is reduced by more than a factor of 4. Prism layers with this feature are encountered in most engineering applications of CFD using automatic grid generation. These plots show details of 3 grids at the step corner: grid 3 with local refinement at the step edge, and the reference Cartesian grid. Approximations for both convection and diffusion fluxes at red faces in non-orthogonal grids are less accurate than approximations at blue faces in the Cartesian grid. In the grid with a local refinement at step corner, the cell aspect ratio is 5.2 times smaller than in the original grid, which leads to a smaller discretization error. This will be shown on the next slide. This plot shows shear stress distribution along channel wall downstream of the step, computed on the 3 trimmed grids and the reference grid. The location of reattachment point, that is, the length of the recirculation zone, is identified by the location of zero shear stress. There are strong oscillations at the step edge in solutions from all 3 trimmed grids, and the recirculation zone is too short. The solution is changing in the direction of reference solution with grid refinement, but it would take many more refinements to reach the reference solution. This plot shows the comparison of shear stress along channel wall downstream of the step, computed on grid free with and without local refinement and on the reference Cartesian grid. Local grid refinement at the edge improves the accuracy significantly, but it also produces a high overshoot in the first cell at the step and is still short of reaching the reference solution. These two plots are analogous to the above plots, only showing pressure instead of shear stress. The non-orthogonality in trimmed grids near step edge leads to an extremely low pressure at the step edge and a too fast recovery. Global grid refinement leads to changes in the direction of reference solution, but at a too slow pace. The local grid refinement results in a significant but not sufficient improvement. Here we are looking at the effects of non-orthogonality at sliding interfaces. The test case is the laminar flow in a mixer shown in this picture, which is described in detail in slides 25 to 30 in lecture 26. One region is attached to the rotating impeller and rotates with it, while the other region is attached to the vessel and fixed baffles. The two regions are separated by a cylindrical sliding interface. Polyhedral grids are used for both regions. These two plots show a small part of the grid in a cross-section through impeller blades. The red grid is from the rotating region and the blue grid is from the fixed region. One layer of prismatic cells is generated on both sides of the sliding interface, but in one grid these prism layers are very thin, while in the other they are much thicker. With a thick prism layer along sliding interface, simulation runs smoothly with under relaxation factors 0.5 for pressure and 0.9 for velocities, as the residual histories show in this plot. With the same set of under relaxation factors, simulation on the grid with a thin prism layer along sliding interface diverges, as is visible from this plot. This is due to the high non-orthogonality as outlined in slide 6. To achieve convergence of outer iterations on the grid with thin prism layers along sliding interface, the under relaxation factor for pressure must be reduced and the number of outer iterations increased from 5 to 8 to achieve the same level of residuals as in this plot. A special case of grid non-orthogonality occurs in Cartesian cells at a local cell-wise refinement interface. The lines connecting neighbor cell centers do not pass through the centers of common faces as shown in this figure. Even for a linear velocity profile, for example in a quad flow, the sum of convection fluxes through the refined faces E1 and E2 is different from the convection flux through the west face W when the exact solution is used with midpoint rule approximation. Here is an example. The velocity u varies linearly in y direction and its convection flux through the west face, assuming that face area is w equal 1 and rho equal 1, is Fw equal rho u squared times area S equal 0.5 squared equal 0.25. On the east side, we have two faces, E1 and E2, and the fluxes through them are Fe1 equal rho u E1 squared Se1 equal 0.25 squared times 0.5 the area equal 0.03125, and Fe2 equal rho ue2 squared Se2 equal 0.75 squared times 0.5 the face area equal 0.2815. The sum of convection fluxes through the two east faces is Fe1 plus Fe2 equal 0.3125, which is significantly more than the flux through the west face. Because a finite volume method enforces conservation, that is, making the sum of the fluxes through E1 and E2 equal to the flux through W, the solution must be disturbed at such interfaces. An example is shown on the next slide. Here are the results of computation of laminar quad flow using second-order approximations and the grid shown in this plot are presented. The exact solution has constant pressure and a linear velocity profile in y direction. Computation on a uniform Cartesian grid with any cell size produces the exact solution. However, when half of the grid is refined, the situation described in the previous slide arises, which leads to disturbances in both pressure and velocity fields. We see in this plot that pressure has a different level downstream of refinement from the level on the upstream side. This plot shows the variation of pressure along the channel computed on 3 systematically refined grids, with grid spacing halved. Errors are obviously reducing by a factor of 4, that is, with second order when the grid is refined. The same is true for velocity variation along the channel presented in this plot. It appears that the hanging nodes approach, see slide 18 in lecture 23 for details, works better at cell-wise local grid refinement interfaces than when non-refined cells along interfaces are treated as polyhedral. Hanging node approach is non-conservative at interfaces, but with an appropriate interpolation when computing variable values at hanging nodes, it would not cause disturbances. In the example from slides 14 and 15, linear interpolation with a hanging node approach would preserve the exact solution of quiet flow on both sides of the refinement interface. Disturbances at cell-wise grid refinement interfaces are especially visible in acoustic simulations. Enforcing momentum conservation in interfaces causing velocity and pressure disturbances, as shown in preceding slide, and these affect the acoustic pressure waves. An example is shown on the next slide. Here, the results of simulation of propagation of acoustic pressure waves in a two-dimensional solution domain with different grids are presented. Pressure variation in the form of a pulse, as shown in this plot, is prescribed on this circular boundary. These two boundaries are treated as symmetry planes, while at these boundaries the velocity is forced over zero using the method presented in section 13.6 in the book. Both velocity and pressure are initially set to zero. Two grids were used. One is shown in this plot with several grid coarsening interfaces with increasing distance from the boundary where the pressure oscillations are prescribed. In the other grid, the cell size from this zone is kept in the rest of the solution domain. The number of cells per wavelength lambda of pressure fluctuation is indicated in each grid zone. On a grid without coarsening interfaces, the solution is smooth, as can be seen in these two plots. The instantaneous pressure profile is taken along this line at time t equals 0.03 seconds. On this grid, the solution is not smooth, as can be seen in these two plots. The oscillations are caused by disturbances at coarsening interfaces, as shown on slide 15 for the quiet flow. In the unsteady flow simulation, those disturbances travel with the wave and after some time spoil the solution in the whole domain. This plot shows the trimmed grid with prism layers at walls used to perform Run's computation of turbulent flow around a circular cylinder at a high Reynolds number. When Cartesian grids are trimmed by the outer surface of the prism layer, sometimes a few small cells between larger cells are created, as at these two locations. This causes a sudden variation of cell expansion ratio. The same happens at locations where the grid outside prism layer is locally refined, as at this location. The effects of sudden grid spacing variation, that is, a large expansion ratio, on shear stress variation along cylinder circumference from the front stagnation point to the rear stagnation point, are clearly visible in this plot. At every sudden change of grid spacing, a disturbance in otherwise smooth shear stress variation is visible. These disturbances reduce when the grid is refined, so they represent a consistent discretization error. This slide shows the same information as the preceding slide, but for the computation of flow around the sphere rather than cylinder. Disturbances in shear stress, which are visible in this plot, are related to sudden changes in cell width at these three locations. With polyhedral grids, Such sudden variation in cell size can be avoided by ensuring that the triangular surface grid is nearly uniform. A two-coarse grid changes the geometry of the solution domain where boundaries are curved, for example, at leading edges of propeller or turbine blades. These two plots show a section through the grid around the ship propeller. In one case, the grid is locally refined around the leading edge, while in the other grid, no attention was paid to the resolution of the leading edge curvature. These two plots show the grid on the suction surface of the propeller blade near leading edge for the two grid types. We see that when the grid is not locally refined along leading edge, the geometry of the propeller near leading edge is not preserved in the discrete wall representation. The leading edge appears very rough and is significantly different than in the cut geometry. This slide shows sections through the grid used to compute the flow around a ship hull. Everybody knows that the grid on hull needs to be relatively fine and that prism layers are needed, but how about the grid coarsening with distance from hull? In this case, the grid is coarsened too fast, with only two cells of one size before coarsening. This should be avoided. In this grid, the coarsening is also too rapid. It is desirable to keep at least circa 8 cells of one size before coarsening, as is the case in this grid. Grid quality can be quantified by evaluating scalar products of 4 unit vectors, which are indicated in these plots. Vector D connects the cell center with the center of the neighbor cell. All vectors are normalized to unity. Vector A connects cell centroid with face centroid. Vector N is orthogonal to the cell face at its centroid. Vector B connects centers of two neighbor faces, that is, faces which share an edge. In an ideal situation, for example, on a uniform Cartesian grid, the scalar products of these unit vectors result in the following relations: d dot a equal 1, d dot n equal 1, a dot n equal 1, and b dot n greater than 0. If a dot n is less than 0, the centroid is outside the cell, as in this case, which is unacceptable. If b dot n is less than 0, the neighboring cell faces are facing each other, which is undesirable. If such a situation is encountered, the cell should be split along the edge M, common to the two neighboring faces. Several other undesirable grid features are shown in these figures. If the top face of a Cartesian cell is rotated, the side faces become warped. If one face is sheared, the non-orthogonality arises. If tetrahedral or in 2D triangular cells are squished near a wall, high non-orthogonality becomes a problem. With unstructured grids made of tetrahedra, this problem is avoided by creating prism layers along walls, with a gradual expansion of prism with distance from wall. The height of the first tetrahedron attached to prism layer should not be more than twice the thickness of the prism with which it is sharing a face. The warpage of a cell face can be checked by triangulating the face and evaluating the ratio of the magnitude of surface vector divided by the sum of areas of all triangles. The ideal value of this ratio is 1.0, which corresponds to a planar surface. The smaller the ratio, the larger is the warpage. Here is a summary of this lecture. In complex geometries, typical of industrial applications of CFD, the grids generated automatically or semi-automatically by the software may contain zones of poor cell quality. This can affect both convergence of iterations and accuracy of solutions. It is important to use all possibilities to improve the grid quality by adapting its design and local refinements to the geometry and expected flow features. Often, one first performs computation for one grid and then optimizes grid design according to observed flow features in the first simulation. The most critical grid quality issues are cell non-orthogonality and wrapping of prism layers around sharp edges. Anisotropic local refinement at sharp edges helps to reduce the errors. Sudden changes in cell size, that is, large expansion factors, also negatively affect the accuracy of solutions in most public and commercial CFD codes. It is desirable to keep the expansion factor, especially in prism layers at walls, not higher than circa 1.25.